All right, we're going to now use the fundamental theorem of calculus in order to find these definite integrals. And when the antiderivative is easy, definite integrals are now easy thanks to this fundamental theorem of calculus. There's no more Riemann sums, no more limits and adding things together. We just find an antiderivative. So let's start with A, integral from 0 to 2 of 3x squared plus 2 dx. The antiderivative is x cubed. So x cubed over 3, and the 3's cancel, plus 2x, and we're going to go from 0 to 2, which means we evaluate that at 2. 2 cubed is 8, plus 2 times 2 is 4, minus that evaluated at 0. I recommend always using these parentheses to separate the evaluation at one point versus another. That way we'll get the signs right. So that's just 12 minus 0, or 12. So that's the area under that curve from 0 to 2. The next one we have, B, is an integral from 4 to 9 of 1 over the square root of x plus 1 over x dx. So again, antiderivative, 1 over the square root of x, that is x to the minus 1/2. Right, like that, it's easier to use the power rule on it. So x to the minus 1/2 becomes x to the 1/2 over 1/2. So that's 2x to 1/2 plus the natural log, the absolute value of x, is the antiderivative. I didn't write the plus c on part A. I can write the plus c or I cannot, but it doesn't matter because it subtracts out. When I evaluate it and subtract, it just subtracts off. So you don't have to write the plus c if we're doing a definite integral because that constant's just going to subtract out. So there's my antiderivative. I'm going to evaluate that at 9 and 4. The square root of 9 is 3. 3 times 2 is 6. So natural log of 9 minus square root of 4 is 2 times 2 is 4 plus natural log of 4. I dropped the absolute values since 4 and 9 are both positive. It doesn't matter. That's what happens most of the time with natural logs. 6 minus 4 is 2 plus the natural log of 9 minus the natural log of 4, which we could write as the natural log of 9 over 4. Although that last step wouldn't be essential for the answer. It's just more compact. So again, antiderivative, evaluated at the endpoints, subtract. This is how we find definite integrals if we know the antiderivative. So 0 to pi fourths, secant squared of x dx. The antiderivative of secant squared is tangent. So we get tangent of x from 0 to pi fourths. The tangent of pi fourths, we can draw it if we need to, but 45 is a 1, 1 square root of 2 triangle. Tangent is opposite over adjacent, so 1 over 1 is 1. So we have 1 minus the tangent of 0, and the tangent of 0 is 0. So the answer is just 1. There's exactly 1 square unit of area under the curve secant squared of x from 0 to pi fourths. So that's it. It's great, this fundamental theorem of calculus. We find antiderivatives, we evaluate them at the endpoints, we take the difference, and we have the definite integral. No more Riemann sums, no more rectangles or limits. This is how we do these things now whenever we can find that antiderivative.